if you recall, 2 classes ago, I talked about something called the Tomita-Takasaki theorem. I mentioned the theorem saying, if you look at the operator, that basically, you look at the map, the adjoint map, x square and x star, but at the level of Hilbert space, we think of x as x hat, sitting inside L2M. Then, by studying that operator which sends x to x star, the theorem says that conjugate linear mapping is in fact a closable operator. That means it has a closed extension, and that closed extension will have a polar decomposition where there will be an anti-unitary part and a positive part. And the statement was that the anti-unitary part would conjugate the one-Neumann algebra to its commutant. And there's something about the other positive part also. And this whole thing so that statement of the Tomita-Takasaki theorem, I want to prove in the baby case when you are working with a tracial state. When you assume that you have a finite one-Neumann algebra, one which admits a faithful normal tracial state. So we're looking at such a one-Neumann algebra M, and we're looking at the GNS construction which leads to the space L2M tau. And because tau is faithful, the associated representation pi tau embeds M. That's a faithful representation, right? So we think of M itself as sitting inside L2M, like we think of L infinity of a measure space as sitting as a subalgebra of operators on L2 via multiplication, left multiplication operator, but in the commutative case it doesn't make a difference, left multiplication or right multiplication. And in the GNS construction, we saw that when you define the inner product in L2M tau by phi inner product of x hat y hat equals phi of y star x, when you bring the right side over the second coordinate to the left side as the adjoint, then the left multiplication defines can be extended to bounded operators on the whole space. But the right multiplication in general will not be. But those problems can be got rid of if one dealt with a tracial state. Then, so we're assuming that tau faithful normal tracial state. And the way to see what I'm saying is, so first we defined a mapping J from L2M to L2M. Such that J of x hat equal to x star hat. And we saw that this was conjugate linear, and anti-unitary. And in fact, So we started with this equation and observed that this was norm-preserving, and hence it extends, it's a norm-preserving map of a dense subspace all to itself. So it extends to a bounded conjugate linear operator of the big Hilbert space, and because on this dense subspace, this J is an involution, that is J squared equal to identity. The same will persist even for the continuous extension to all of L2. Right? Conjugate linear and J squared is 1. A norm-preserving involution. Right? J squared is 1. But that means that, in fact, see, I told you that when you have conjugate linear operators, the adjoint of the operator, the defining equation will have a funny form. It won't look like the adjoint equation for linear operators. Right? So the equation is that, see, the relation relating the adjoint, the operator is going to be this. Right? So now, in particular, if you look at J star y hat, the product x hat, then that is going to be equal to J x hat y hat. Right? But this I can think of as, actually you can write down the equation straight away. Okay, this I can think of, see, because J is norm-preserving, I can write this as J squared x hat, J y hat. Right? So what we see is that this is equal to x hat, J y hat. So what I'm trying to say in my muddle-headed fashion is that, in fact, J equal to J star. Because, see, what is, let me start the other way. Let me start with J x hat y hat. Huh?
Jx hat y hat equal to x hat jy hat.
This equation will tell you. This equation tells you, because the adjoint equation defines the adjoint uniquely when the things are bounded operators. So this equation tells you that J equal to J star. Or in any case, J squared equals 1 means J is its own inverse. So this is like equal to J inverse. See, for bounded linear operators, if an operator satisfies this equation, then that would have to be self-adjoint and unitary. Right? J squared being J inverse will mean unitary, and this is self-adjoint. So for the in the conjugate linear case, this will translate into J being self-adjoint and anti-unitary. Okay, so I wanted to convince you last time that see in L2 M tau by definition 1 hat is a cyclic and separating vector for M as well as for M prime. And because it was cyclic and separating for M, the equation J of x hat equal to x star hat is well defined and 1 1 and norm preserving and everything. It is norm preserving and 1 to it is 1 to 1 and well defined because it is cyclic. 1 hat is cyclic and separating for M. But 1 hat is also cyclic and separating for M prime. So one could even try to define a similar equation sending x prime hat to x prime star hat. That would also be a well-defined conjugate linear map defined on a dense space of a dense space onto itself. So it will extend to an anti-unitary operator exactly as before. I'm saying that operator is the same as this operator. So I want to claim that J, so claim is that J of x prime hat equals x prime star hat for all x prime in M prime. Okay, so why is this true? So I check it against, I want to say the two vectors are the same. It is enough to say that their inner product with everything from a dense subspace are the same. So I look at what I get when I take an inner product against an x hat. Where x is in M. Okay, by definition of the, because J is its own adjoint, the adjoint equation will tell me that this is equal to Jx hat, sorry, x prime hat I'm having here, x prime hat. Okay. Okay, which is what? Which is x star hat x prime hat. But now I think of this as x star of 1 hat x prime of 1 hat. Actually, I shouldn't write x prime hat. That doesn't make sense. Sorry, in all this, I defined x hat only for things in M. X hat was the image of x in the map from M to M mod the radical of the trace. Right? So x prime hat, so here what I mean is that x prime hat equals x prime of 1 hat. X prime of 1 hat makes sense because 1 hat is the 1 of M is what one is talking about. There is the identity operator on till 2M. Okay, so this is what we have. So then I can pull the X prime over to this side as X prime star X 1 hat 1 hat.
X star.
Huh?
X star and X star.
X star, sorry. But now X prime and X commute, and so they are adjoints also. So I can turn it the other way, and then pull the X over to the other side as X, and I can repeat everything with just X and X prime interchanged. Equal to ... and finally I will come back with just X and X thing replaced. So I want to say Jx dash no.
First is X star.
Okay, so if we put that over, then we'll have, okay, let's go backwards. So this is X star 1 hat sorry, because I want to move this inside, right? X star 1 hat and X 1 hat. That itself does it for me, because I've shown that I've shown that J X dash 1 hat X hat equal to X prime star 1 hat X 1 hat. But things like X1 hat are dense, and therefore Jx prime 1 hat equals X prime star 1 hat. Okay, so why is this useful for us? Because we saw last time, again that was just a simple computation, that if you take what we saw was that if you look at J xj of y hat equals y into yx star the whole hat. Right? Last time we did this computation, right? I wrote Jx star j y hat equals yx the whole hat. So I'm just writing with x and x star interchange. So one has Jxj of y hat is yx star the whole hat. So, and from this I deduced, because left multiplication and right multiplication commute. See, this is something like a right multiplication. Y hat goes to yx star the whole hat. Whereas the way x acts is x times y hat will be xy hat. So this will imply, I showed you last time that zjxj y hat equals z y x star the whole hat. Whichever way you want to combine the triple product. So that can be written as saying this is equal to jxj of zy hat. That is that jmj is contained in M prime. This is true for all y hat. So the operator, without the y hat, the equation is still true as operators. That means jxj commutes with z for any z and for any x in M. That means anything in jmj is in M prime. So this proves that jmj contained in M prime. And this only used the fact that j sends x hat to x star hat. Since I proved the same thing for M prime now, similarly j x prime 1 hat equal to x prime star 1 hat will imply that j x prime j of any y prime hat equals y prime x prime star the whole hat. And using the fact that one hat is cycling and separating for M prime, one concludes from this that j M prime j contained in M prime prime, which is M. So finally, these two inclusions together these two things will imply that jmj is M prime. What's the problem shown? You kind of so this is the first assertion in the Tobit-Lagrange theorem, that jmj equal to M prime. But there was a delta that came from taking the polar decomposition of what I've called J. In fact, in the original statement of Tobit theorem, I had said you define an operator S by sending x hat to x star hat, then call that S naught, then S naught has a closed extension, and take the closed extension S, look at its polar decomposition, S equals j delta to the half, and then it said something about delta. The delta to the IT will conjugate M into M for all t. But in this case, that S is the same as j. S is what I called S in the Tobit theorem, now I am calling j. But that is because I know, I know before itself that delta is going to be 1 in this case. because tau is the trace. Delta is 1, so that second part of Tomita theorem is trivial here. The strength of the Tomita theorem is that it gives you, for any one Neumann algebra, need not be finite also. It gives you.
It is 1 because AC equals to J.
Yeah.
S equal to
J,
R.
in this case.
So J square equal to 1.
So because of the uniqueness of the polar decomposition, if you want, so delta is 1. Or delta equals S star S, but S star is equal to S because S is self-adjoint. S is equal to J. And so basically you see you must think of M prime. See, M prime is JMJ. What does JMJ do? It kind of behaves like right multiplication. What it does to a y hat is to send it to a yx star hat. Jxj is right multiplication by y star, x star. That is why in that other theorem I was talking about left bounded and right bounded and so on. Things in M should be thought of as left multiplication operators. A vector is left bounded if it is bounded for this left representation of M. Vector is right bounded if it is bounded for the action from this side. And the theorem that I was trying to prove last time was that I defined left bounded vectors, right bounded vectors, and showed that being left bounded is the same as being x1 hat for some x in M. Being right bounded is equivalent to being x prime 1 hat for some x prime in M prime. And consequently the set of left bounded vectors is exactly M1 hat. The set of right bounded vectors is M prime 1 hat. But now because of this, I am able to because J 1 hat is equal to 1 hat. And now that I proved that JMJ equal to M prime, it follows that M prime 1 hat equals JMJ 1 hat, which is equal to JM 1 hat, which is equal to M1 hat. Right? So I'll just repeat this. So JMJ equal to M prime implies that M prime 1 hat equal to M1 hat. That is, but this is M prime 1 hat is set of right bounded vectors. Whereas this is the set of left bounded vectors. And so in the general case, the non-commutative case also, when you have a trace, one has seen that the left bounded vectors and right bounded vectors are the same and that they are precisely the thing that come from M, which is the statement about L infinity that I've been harping on for a long time. Elements in L2 which act as bounded vectors in the sense that norm of what does bounded vector in L2 mean? F in L2 is a bounded vector meaning this just means it is left bounded for the action of L infinity. Right? So is the statement that there exists constant positive, so then norm of phi F2 norm is bounded by, let me call it F phi. No, I call it phi. It is equal to constant times norm phi 2 norm. And this was that if you compare this with my definition of left bounded. Psi is left bounded if there is a constant such that norm of x psi is bounded by k times norm of x hat. So that is the statement that I have been using before also to prove things about the representation of L infinity. And so one has the exact analog in the finite one-Neumann algebra case. So now I want to give you an example, an important example of a finite one-Neumann algebra. Of course, I can take n by n matrices. That is going to be a finite one-Neumann algebra. In fact, any finite direct sum of matrix algebras, M3 direct sum, M17 direct sum, M5, each of them has a trace, and so I just add the traces. I will have a trace on the whole thing, and so I will have the thing will admit any finite dimensional one-Neumann algebra, in fact, because it admits a representation on finite dimensional Hilbert space actually, admits a trace because it sits inside a matrix algebra. Right? So any finite dimensional embeds inside an Mn. For some n, in fact you can take n to be dimension of M. This is the left action of M on itself. You're taking M hat and you're taking the left action of M on itself. Why is it faithful? Because M has an identity, and that is the star representation.
This is the trace of matrix.
Yeah, that's what I'm saying. If you take any finite dimensional one-Neumann algebra M, then how do I prove this thing?
M is some subset of PH. So
And but that BOH could be infinite dimensional.
dimension of M is what?
M is a vector space, right?
What is the action? What is the action?
So I'm saying any finite dimensional one-Neumann algebra can in fact be embedded inside Mn, where n is the dimension of M.
So what is definition of dimension of M? Dimension of M
M is a vector space, no? So I look at the action of M on
You have to act on the basis of your M as a basis.
M acts on M itself by left multiplication.
So to get the
But how do I get a star on this thing? So you take any state on M. M is a C-star algebra. It is a finite dimensional C-star algebra. So it does have states. Because why does the finite dimensional mononomial algebra have states? Because I guess I haven't yet proved this thing. You have exactly as for measures, you have this decomposition. Any element of M lower star can be written as it will have a Cartesian decomposition first. Okay, so let me take this. So suppose you take phi in M star. Then actually you can do this for any you can have any C-star algebra actually. Take any bounded linear functional on a C-star algebra. Then I want to define phi star to be, what do you think I should define it as? Is that linear? This we have A star, the whole thing bar. Then you can check that this is linear, and it will have the property by definition that phi star of A star, if I swing things around, phi star A star will be phi of A bar. Right? From which we see that phi plus phi star by 2 will take real values on self-adjoints. Is real on self-adjoints, so-called Hermitian part of A. Okay. And then comes the next part where you want to say that any phi in, if I now have a real, such a real functional, I can write that as a difference of two positive functionals. Like in measure theory, if you have a real finite real measure, a signed measure, you can write it as a difference of two positive measures. And so that requires some proving here, because A sits inside B of H. Let me prove it at least for von Neumann algebras. We know that if M is the von Neumann algebra, so M von Neumann algebra, and I'm only looking at von Neumann algebra which admit actions on separable Hilbert space. That is, or another way of saying it is, with separable pre-dual. Those are the only one-nominal algebras we look at, just as the only Hilbert space we look at are the separable ones. So any such one-nominal algebra will admit an action on be a wage for separable H.
M star is separable or H separable? Same.
The same thing. Demanding that M lower star is separable is the same as saying that M admits a faithful representation on separable Hilbert space. Namely, you take, see, the point is that if you take an element of M lower star, which is positive, then that state will give you a normal representation of M. But why does M star have positive states?
You can, if H is separable, then M star, you can make it separable. W's, eta, those would be the basis.
It's not a basis. Those aren't independent. That's only a spanning set. That's sigma weakly spanning. Okay, I think this will take us too far afield. I don't want to get caught in this topological subtleties for now. So let us just say that for the case at hand, I can kind of bluff my way through in the following way. If A is a C-star algebra, and if A is finite dimensional, then I claim that A admits, that we've seen that proof by taking that if A star is separable, then A can be represented on separable Hilbert space faithfully. That is what we have seen. That is the so-called non-commutative Gelfand-Naimark theorem. And so, but if M is finite dimensional, then upper star, lower star, everything is the same. M lower star is finite dimensional because its star is M, which is separable, which is finite dimensional. M lower star into M upper star, you have an isometric inclusion by Hahn-Banach. But because they are finite dimensional, M upper star is also finite dimensional. And so this M lower star, M upper star, they were all of the same dimension. So they're all the same thing. So if I think of M as a C-star algebra, it has a faithful state. That state is automatically normal. And so I have a representation of separable. So I have a faithful normal state. So I have a representation on B of H where H is separable. No, what do I want to say? No, I want to say that if M, this implies that M admits this is something I already observed, a faithful normal state. right? Because I can take phi equal to summation 1 by 2 to the n, this omega Cn. But there is the vector omega xi I am writing for the vector state determined by xi. And Cn is an orthonormal basis for each. Why is this faithful? Because phi x is, if x is positive and phi x is 0, then this will say that x xi n must be 0 for odd n, and so x xi n itself must be 0. And if that is true for an entire basis, then x must be 0. So if M admits a faithful normal state, then I take the GNS representation for M. There because phi is faithful, the radical of phi is going to be trivial. So the associated Hilbert space H phi will just be A hat. A thought of as a Hilbert space with this inner product. That means the dimension of that H phi is the same as dimension of M. And in particular, there is finite dimension. So, if M is a finite dimensional polynomial algebra, at the end of the long story, I can embed that into an MNC. Once I've embedded, but in MNC, I take the usual trace. Or I must normalize so the trace of 1 is 1. I take 1 by n times the matrix trace. That will be a faithful normal tracial state on all of Mn. In particular on any star subalgebra of Mn. So in particular if you have a finite dimensional polynomial algebra, it can be put inside MNC where n has the same, n is the dimension of M.
So these phi and that trace, there is a relation?
Huh?
That MNC trace and these phi?
No, I don't know that this phi was positive was faithful to start with. This is a faithful state on M, with which I did the GNS representation, and then because this phi is not necessarily a trace. The phi was just any faithful normal state on M. But because of the finite dimensionality, we are able to conclude that there in fact exists a tracial state, faithful normal. And hence it is a finite polynomial algebra, as it should be, a finite dimensional one. If that is not finite, then who will be? Okay. So any finite dimensional polynomial algebra is okay, I think it's worth, at least for you to get this exercise. You work out what if okay, if M is sitting in MNC, one-dimensional algebra, Define tau of x to be 1 by n summation xia. Just the normalized matrix trace. So this is going to be a faithful normal tracial state on M. Okay? Is a faithful normal.
But it depends on the representation. You have taken any phi and you have got an MNC. So you will get different xi. When it's independent of h, you have to do that.
I'm saying that it can be represented on A, B of H in finite dimensional H. That's all I'm saying. But anything else will look like any other faithful normal representation. Actually, the theorem will say that 82 something will actually be unitarily equivalent. But that is at the end of a long story after doing a lot of hard work with normal linear forms on monomial algebras. Okay, but I want you to check that A model for H tau pi tau psi tau is for H tau I just take A itself. Let me call this A. Because in finite dimensions, 1 C star, everything is same. So what is the inner product on A where xy and take as tau of but that is the inner product, right? On A hat. You're just taking the trace of xy star, and should I do? No. Let me do. No, let me take A equal to MSC. With the inner product being given by this, and what is pi tau? It is just pi tau x or y is just xy. They just left multiplication by x. And psi tau is identity. I'm just, this is not an exercise at all. I'm just restating the DNA. But to think of it as an exercise, what you should, okay, never mind. So this is not well thought out exercise, but I'll get back to that later. Now let me get to my important example. Suppose gamma is a countable group. It need not be everything, it can be anything. So, for example, you could take gamma to be the integers. So, there are several examples. I can take integers, I can take z power n, or I can take the so-called free group on n generators. Have you seen the free group? What is a free group on n generators? You just take an alphabet of n letters, and then you take all possible words in there, except you postulate that words in the alphabet union the alphabet inverse. So you take elements x1, xn, let me call it u1 and un. And look at all words in u1, un and u1 star. I'm just formally these are just formal symbols now. Words in un, un star, un star, where there is no Hilbert space connotation to the star edge here. And you demand that in such a word, the moment you have a ui star or a ui star ui, then you cancel them out. So you think of that as that inverse. But those are the only relations. And then prove that what you have is in fact a group, and it will have the property, it will have a universal property that if you take any group with any n elements, there will be a homomorphism from this group to that group, which will send these generators to those n elements. Any group with n elements is a quotient of this free group. So there are quite a few interesting examples. Or I can, for example, take GLN of Z2 or ZP or ZQ, where Q is any prime power. ZQ is a field, GLN ZQ is just the invertible n by n matrices with entries coming from ZQ. This is actually a finite group. This is a finite group. But you can have any group generated by n element will be a countable group because the quotient of the free group. You take any n invertible matrices and take the group that they generate. That can be quite complicated. and that will be an example of such a gamma. Okay, given this gamma, one does the following thing. So, write L2 gamma some Hilbert space with orthonormal basis. I will just call it 1 sub S or 1 sub T, T in gamma. Or I'm saying you think of gamma as a measure space, it is a countable set. Think of it as a measure space and think of 1 sub D as the indicator function of just the point T. And then okay, there are different ways of doing it. So the simplest way is the following thing. So define okay. See, the set of all 1t as t varies over gamma is an orthonormal basis. So for fixed tests, there is this change of variable 1 sub st t in gamma is also going to be an orthonormal basis. This is just the same basis written in some different order. Right? In fact, I can define a mapping. So in fact, if you take any two orthonormal bases for Hilbert space, there will be a unique unitary operator which will send this basis vector to that basis vector, to the same thing. So I'm saying there exists a unique, let me not say S, I would write S inverse. No. That's correct. So I want to say there exists a unique unitary operator on L2 of gamma such that US of 1t equals 1st for all st, for all t in gamma. Right? Because this is an inner product preserving mapping, and so it is the external unitary and so on. Application of KRP lemma. Right? So this is an orthonormal basis, that is also an orthonormal basis. Okay. And the thing to note is that S going to US is a group representation. This is what is called a unitary representation. A unitary representation of a group is by definition a homomorphism from the group into the group of unitary operators on some Hilbert space. That every US is a unitary, and I'm asking you to observe the trivial statement that US times UT equal to UST. That is, that S coordinate US is a homomorphism. Yeah. Then one defines I'll call it L gamma equal to the one-Neumann algebra generated by all these US's. Actually, let me not call this US. I'm sorry, I've changed my notation. I call this lambda S. Lambda for left. Because there is left multiplication. T going to ST is left multiplication by S, so we call it lambda S. So let this be, so this is a collection of, this is a group of unitary operators, so this is closed under adjoints. Right? The adjoint of lambda S is lambda S inverse. S in gamma double prime. So I have a self-adjoint collection of operators. We take any group of unitary operators, then certainly self-adjoint. And if we take it double prime, there will be a one-Neumann algebra. So what is this? So this is by definition the I'm defining the
it is for L2. L represents for L2.
No.
Left.
L is for left. So this is called the, if you insist, okay, I'll come back later to the terminology and reason for the notation. So another way of saying this is, see what is the star algebra, what is the algebra generated by, see, the one-Neumann algebra generated by this group is going to be the, you take finite linear combinations of these elements, that set will already be closed under products. Right? Because lambda S times lambda T is lambda ST. So we take any finite linear combination of the lambdas, the set of finite linear combinations we take the linear span of all lambdas S and gamma. This is a star algebra, unital star algebra. And contains unit because if I take S equal to 1, that is the identity. And if I take the linear span of all that, that is already a unital star algebra. So there is nothing but the SOT closure, WOT closure, whatever you want. So that's all let me say. The closure SOT. Okay. And but exactly same thing if I want to look at right multiplication. So See, there exists a unique unitary operator, rho t in US into gamma such that rho t of 1s equal to 1 of, see, remember I want it to be a group, I want S I want T to rho T being to be a group homomorphism. Whereas right actions will not preserve things. So I need ST inverse. And T going to rho T is also a representation, unity representation. Actually, when I say unity representation, I already said, I think once before, this means that it must be strongly continuous. For every psi going to rho T psi must be continuous. See, to say you have unity representation on infinite dimensional Hilbert space, what you mean is that for each vector psi, T going to ut psi must be continuous. But the UTs are all unitary, so they have normal, they are uniformly bounded. So to check that T going to rho T is SOT continuous. It is enough to check it on a basis. But what does T going to rho T, what does this do on a basis? On the standard basis, 1s will go to 1 ST inverse. And actually in this case, sorry, ignore what I said because you're talking about discrete groups. And there's no topology. Every map is automatically continuous. So this unity representation, it just means group homomorphism. Okay, so this is a unity representation, very good. And so let me call this as M. This is the so-called left group Neumann algebra. Okay. Okay. So the point is proposition to define a function of tau of x equal to x 1 sub 1 1 sub 1. This one is the identity of the group. Maybe you want to call it E. Right? I'm saying you look at the vector state determined by the identity element of the group. Then the statement is that this for x and m defines a faithful normal tracial relation. And the associated, what is the, there will be an, if that is true, there will be an associated J mapping, right? Maybe I should call it J sub tau. There I should have called it J tau to denote the dependence of the J operator on the tracial state you're working with. What does this J tau do? J tau of see, the one-dimensional algebra M is generated by the lambda S's. And in fact, the lambda S hats form a dense subspace of the Hilbert space. I mean, they form bases. What is lambda S hat? What I'm saying, see what I'm saying is that what I'm trying to say is that L2 gamma idem 1 sub 1 is the GNS triple for M. For this tau, yeah. So I'm saying for tau I should have said. So we need to verify that this tau is a faithful normal trace and so on. Okay. And what does J? You can guess what J tau is, of 1s is going to be. One s is what it is, lambda s of 1 hat. The 1 hat is 1 sub E. Okay. What is lambda s of 1e? It is just 1s. What is lambda s of 1e? Of 1e is going to be 1s. Right? So this is J tau of lambda s hat. That is J tau of, so what is that? That is lambda S star hat. And what is lambda S star? it is lambda S inverse, because lambda S is unitary. And what is the lambda S inverse hat? There is just lambda S inverse acting on one hat. It is going to be 1 sub S inverse. The J operator is the thing that sends 1s to 1s inverse. It is the reflection. Like if you think of gamma equals the integers, it will send n to minus n. It is that anti-unitary operator which sends, on this basis it looks like inversion. And you can see that J what is J lambda S J of 1t. We'll just do a computation and see. J will send that 1t to 1t inverse. Then you will have 1 st inverse. And then you will have one of the inverse of that. So 1 ts inverse. Which is rho s of 1t. Right? So
M dash is R.
so M dash is rho m double prime. So the theorem that we proved, once I verified this, convince you that this is the faithful normal trace and that this is the standard form, that there is a genus space and so on, will show that the commutant of left multiplication operators is exactly going to be generated by right multiplications. So maybe I shouldn't get into this. Okay, Remy will do this next time. So let me check all the details. So one can show that if gamma has satisfies the following property, then it will always be a factor. Namely, if it has a property that all conjugacy classes are infinite. Yeah.
Cardinality
Of every conjugacy class in the group should be infinite. It must be an infinite set. The cardinality of any conjugacy class must be infinity. See, for example, an example of such a gamma will be I guess. See, if you take You know the permutation groups. You denote by Sn, I am calling it sigma n. Huh? Oh, sorry. Oh, sorry. Okay, I write sigma n for the group of permutations or n symbols. Those n symbols I think of as 1, 2, 3 n. So look at sigma n, which is permutations of one, two, three n. As sigma sub n. Now I think of this as sitting inside sigma n plus 1 as all those things which fix n plus 1. That is, they only move 1, 2, 3 n. So such a permutation I think of as something in sigma n. I can also think of it as something in sigma n plus 1. So this forms an increasing chain of finite groups. So let us take the union. Let me call this sigma infinity. So what is this? This is all those permutations of the positive integers with the property that they move only finitely many integers. After some stage, they just fix all the integers. These are the permutations which move only finitely many integers. And you know that in sigma n, two permutations are conjugate precisely when
Have same length, same cycle. Same number.
same cycle structure they must have, correct? So it is clear that the cyclic permutation 1, 2, 3 and the cyclic permutation 15, 19, 47 are conjugate in sigma infinity because they're both cycles of rank 3. Right? So in fact, if you take any element of sigma infinity that lives on some finite n, so if I conjugate it by permutation that pushes this all the way to the right, beyond that n, I'll have something which will commute with this. If this permutation lives only on 1, 2, 3 n, and this lives only after n, then these two will clearly commute. Right?
Result is coming.
And these two will be conjugate. So what I'm saying is that any element of sigma infinity, if it is not equal to 1, that if it has a non-trivial cycle in its structure, then in its conjugacy class I can find infinitely many things by just moving those cycles farther and farther apart, so that they'll all be distinct permutations, they will all be conjugate, and they will even commute actually. So this is an example of a thing which has that property that all conjugacy classes are infinite. All conjugacy classes other than identity. The identity, of course, with conjugacy class is trivial. For any such group, they are called ICC groups, infinite conjugacy classes. Every ICC group, is an example of something we've been talking about, something called a 2-1 factor. And is a factor. Forget 2-1. I'm saying it is a factor. M intersect M prime is trivial. And the trace, and you know that a 2-1 factor comes with a unique trace. This is infinite dimensional. If the group is infinite. So you have 2-1 factors. Because the other, if it's not a 2-1 factor, it must be a matrix algebra. And so these give you lots of examples of 2-1 factors.
It is finite.
Huh? I'm giving you a trace on it, no? I'm giving you a faithful normal tracial state. That automatically means that it is a finite factor. Okay, so I must apologize to some of you to whom the last bit may not have made sense, all this factors and so on. But that is something you will eventually have to learn.